Now, good morning, everyone. This is lecture number 2 in kinetic theory of gases. And I guess in the last class, we were dealing with gas laws. We had dealt with Boyle's law, Charles' law, Avogadro's law, Dalton's law of partial pressure and all that. We had also dealt with ideal gas law, PV is equal to nRT, where N stands for the number of moles. I hope you remember this. Capital N stands for the number of moles. We have also seen one more version of that. PV is equal to NKT, where small n is the number of molecules or the number of atoms, and K is Avogadro's. K is Boltzmann constant. Do we all remember this? Can I have some raise hand that we understand this? Okay. We had dealt with some questions here on these gas laws, and you will find one or more of these questions coming in your exam. Having said that, let us now move on to today's class. And in today's class, what we are going to do is to go ahead and do this kinetic theory of gases. We have seen some basic concepts of this kinetic theory of gases. Kinetic theory of gases. Gas molecules are spherical in shape. They are very small. Distance between them is very large. They are constantly moving. They are colliding. All collisions are elastic. We had seen some assumptions of that. That is the assumptions of the kinetic theory of gases. Now, based on that assumption, we can arrive at some very important derivations and formulae, and we are going to do those derivation and formulae. We are not going to derive anything. We will just be seeing the final formulae as they come in. We'll only see those final formulae as they come in, and this is what you have to understand and remember the diagram. We are not doing the derivation. That is not important. What is important is what you see on your screen right now. What do you see on your screen right now? You can see the expression for pressure of an ideal gas. I hope you understand this expression for pressure. Pressure P is equal to 1 by 3. This 1 by 3 wala factor comes multiplied by capital M. This capital M is the mass of the gas. This V is the total volume of the gas, and this V RMS square is RMS velocity ka squared for the gas. Total mass divided by total volume becomes your density. So you have the formula P is equal to 1 by 3 rho into VRMS square. This is the formula that you get, which relates pressure with density and the RMS velocity. How this formula is derived, I'll just give you a hint. We assume that there is a cubical box. A gas is kept in that cubical box, and then we find how many particles are colliding. We find their change in momentum. From that change in momentum, we find out the force. From that force, we find out the pressure, and it's a long derivation. We will do the parts of that derivation, and you will remember them as important points, because these same points will come in your examination hall. This is the first point that you must understand. P is equal to 1 by 3 rho VRMS square. There will be another versions of these of this formula. We'll do those versions as they come. Special points. All these special points are questions. Average number of molecules which are hitting any particular wall or which are moving in any particular direction is n by 6, where n is the total. They have used capital N. I will use small n. For me, small n is the number of molecules. So total number of molecules along any hitting any wall will be n by 6. total number of molecules which are moving along any axis, x-axis, y-axis or z-axis will be n by 3. Total number of molecules along x-axis, total number of molecules along y-axis, and total molecules along z-axis, the total number will be same, and that number will be total number n divided by 3 vx square. The average value of vx square, the average value of vx square is equal to average value of vy square is equal to the mean value of vz square, and that is vrms square divided by 3. You will have to remember these things. I'll give you a minute to note it down. Do we understand this? Can I have some raised hands? What we have discussed? I only see one raised hand. What about the others? Right. Please note this down. All these questions will be there. All these points will be there as questions. Note it down. You can write the second point like this. Average velocity square along x is vrms square by 3, or you can write vrms velocity along x, vrms velocity along y, vrms velocity along z-axis is nothing but your total vrms divided by root 3. A question has come on this concept, and that is why you will note it down. I hope you are noting it down. All these important points will come as questions. You have any doubt? Note it down. Okay, you have noted down. So I will move on to the next point. Again, everything is taken from your sheet, and that is why having this sheet is very important. Now here you see a collision of a particle, of one gas particle, one gas atom. You see, you find out how much is the transfer of momentum. It is hitting and it is going back. From that change in momentum, we can find out force, and from that force we can find out this pressure, and the formula is P is equal to 2mv cos theta. Why it is 2mv cos theta? Because once it is hitting, the momentum along x-axis is mv cos theta. When it is going back, the momentum is minus mv cos theta. Total change in momentum is 2mv cos theta multiplied by number. How much number are hitting multiplied by time divided by area will give you the pressure exerted by one atom, or the total number of atoms hitting this wall, and that is the pressure exerted by this molecules hitting the wall. There is a one more case where molecules when hit the wall, they get absorbed. In that case, the final momentum is zero. The final momentum is zero, and in that case the formula becomes mv cos theta into n divided by at. I hope you understand this. Everyone understand this? Can I have some raise hand that we understand this? Okay, please note it down because question will come. Two cases. Case number one, when it is getting reflected. Case number two, when it is getting absorbed. I'll give you a minute to note it down. I hope you have done this. We'll move on to the next point. We'll move on to some formulae. And this is the first formula. This has come many times in the exam. Kinetic energy of gas. They ask you in different ways. They can ask you what is the transitional kinetic energy or average transitional kinetic energy. The answer is half into total mass m into v square RMS. You can write it like this: 3 by 2 into P into V, where P stands for pressure and V stands for volume. This is the total transitional kinetic energy. Do we understand this? Total transitional kinetic energy of all the molecules put together. This is the total transitional kinetic energy of all the molecules put together. You can also write it as 3 by 2 nRT. Do you understand? PV becomes nRT. Do we understand this? Or you can also write it as 3 by 2 NKT, where N stands for the number of molecules in the gas. This is total transitional kinetic energy. Please mark my words. This is total transitional kinetic energy. I hope everyone is understanding this total transitional kinetic energy. Can I move ahead in life? Remember the different terms, because if you get confused, you will get -5. Only you are 100% sure that you get +4 here. Otherwise, -5 is waiting for you and you will get -5. Shall I move ahead in life? Then, as I said, different types of kinetic energies. The first one we saw was total kinetic energy. This is kinetic energy per unit volume, per unit volume, per unit volume, per unit volume. So how do we find out? We find the total kinetic energy is half mv Rms square, and we divide it by the volume V. The total kinetic energy has been divided by the volume V. Do we see this? Half mv square is half v mv Rms square is divided by V. Do we see this? Yes or no? If I divide it by V, I have half rho into V Rms square. Half rho into V Rms square. This is the total kinetic energy, total transitional kinetic energy per unit volume. So transitional kinetic energy per unit volume will be given by this formula: half rho V Rms squared. Please remember this. Please remember this. Please remember this. Please remember this. We also know that this pressure can be written as 1 by 3 into rho r v Rms square. From this equation, if I call this equation as equation number 2, if I call this equation as equation number 3, from equation number 2 and equation number 3, I can arrive at equation number 4. And as it is written, it is a very important equation which has come many times in the exam. Transitional kinetic energy per unit volume, which is also known as energy density, I hope you are noting it, is 3 by 2 times of pressure. I'll give you a minute to note it down. Very important formula. Please don't miss it at any cost. A minute to win it. A minute to win it. Once you are done, please tell me, raise your hands and tell me so that I can move ahead in life. Shall we move ahead in life? Shall we move ahead? Okay. That takes us to the next formula. All these formulas are derived from the same equation, but they are asked in different ways. The first one we saw was total transitional kinetic energy. Then the second one that we saw was energy, total kinetic energy per unit volume. This is molar kinetic energy. This is one name. Or it is mean molar kinetic energy. Basically, it is basically total transitional kinetic energy per mole. You can also remember it like this: total kinetic energy per mole. Total kinetic energy per mole. Total kinetic energy per mole. Do we understand this? Yes, now you can remember it in different ways. So this is the first way. I will call it equation number 5. Equation number 5, total kinetic energy. This is molar kinetic energy. So instead of total mass, you have molar mass, MW. Do we see this MW, or shall I make it bigger? We see this? In first case, it was total mass M. In second case, it was density, mass per unit volume. In third case, it is molar mass. So this is the difference between the three equations that we have seen. Now, if I put the value of this thing, I will not give you this formula because this formula will be confusing to you. Total kinetic energy per mole or molar kinetic energy, wherever you have the term mole, wherever you have the term mole, you will always have R coming. Do we see the relation between mole and R? Yes or no? So this is the formula for total kinetic energy per mole. I hope everyone is understanding this, because in the next one, I can call this formula as formula number 6. So formula number 5 is done. Formula number 6 is done. In the next case, we'll have formula number 7 and formula number 8. In formula number 7, I have total kinetic energy per molecule. Total kinetic energy per molecule. Total kinetic energy per molecule. So basically, I will write it. I will not cut. I will cut this and cut this. I will write this as total kinetic energy per molecule. Understand the difference between all the three, all the four. The first one was total kinetic energy. The second one was kinetic energy per unit volume. Third one was kinetic energy per mole. The fourth one is kinetic energy per volume. And as you can see, fourth is kinetic energy per molecule. And as you can see in blue, wherever you have molecule or molecule per molecule, you will have K coming into the picture. Do we see this? Molecule and K, how they are related to each other? Yes or no? Well done, well done. Please note it down. I'll give you a minute. You can win it in that minute. Let me know when you are done so that I can move ahead in life. You are done, so I'll move ahead in life. The next one is kinetic energy per gram. I have not seen many questions of this, but there could be one or two questions that has come in past. Per gram, per gram, per gram. So the formula becomes like this. This is formula number, I think 7, I think 7 or 8, depending on from where I see. This is formula number 8. Kinetic energy per gram is 3 by 2 RT divided by the molecular mass MW, or 3 by 2 KT divided by small m. Small m is the mass of one molecule. You can write this formula as formula number 9, which is the kinetic energy per gram is directly or inversely proportional to the molecular mass. This is how the graph looks like. Kelvin scale, the graph starts from 0. Please remember this. Celsius scale, the graph does not start from 0. I hope we have discussed this many a times. I'll give you a minute to draw these things. Most of the things, in fact, all of the things in this chapter is all about you remembering. If you make a mistake, you get -5 straight away. Why I'm calling it as -5? Because Any question that comes from kinetic theory of gases should be done, has to be done. If you can't do it, that means you have lost not 1 but 4 more marks, and that is why it is -5. Have you done this? Next point. Except at 0 Kelvin at any temperature, the order of kinetic energy. We have seen the different types of kinetic energy. The order is here. E standing for kinetic energy per mole, EM standing for per gram, and E average probably stands for per molecule. I hope you understand this. No one is going to ask you this, but this is just at a common temperature for all ideal gas. E and E bar are same because it is 3/2 RT or 3/2 KT. So E is 3/2 RT. E bar is 3/2 KT. E bar is per mole. Sorry, this is per molecule. This is per molecule. This is per mole. And this is per gram. So for any given at a common temperature, E and E bar per mole and per molecule are same, but EM per gram is different, and it depends on the nature of the gas. It is inversely proportional to the nature of the gas. It is inversely proportional to the mass, molecular mass of the gas. Do we remember this? For thermal equilibrium, that means they are in the same temperature. When you have thermal equilibrium, the temperature of all the gases would be same. They might ask you to find out this common temperature of the mixture, and in the next slide, we will see the formula for the temperature of the mixture of the gas. This formula is found on the basis of law of conservation of energy. We will not go into how this formula is derived. We will simply write the formula. Are we ready? This chapter is all about formula revision and formula remembering. If you can remember these formulae, bacha, it is going to help you not only in physics but also in chemistry, because this chapter is common for physics and chemistry, and that is why we are going to such lengths to remember this. Now, if you have to find the common temperatures of the temperature of the mixture, this is the formula for finding out the common temperature. If they have the same atomicity, if they are monatomic, the formula is this: N1 standing for the number of moles of the first one, T1 standing for the temperature of the first one, N1 T1 plus N2 T2 divided by N1 T1 N1 plus N2. If they have different atomicities, then you have F, where F is known as the degree of freedom. Now, what is this degree of freedom? We will come to that degree of freedom in the next class. Right now, you will just remember the formula. If they are of different atomicities, then you have to find out the degree of freedom. What is the degree of freedom? For a monatomic gas, the degree of freedom is 3. For a diatomic gas, the degree of freedom may be 5, maybe 6. We will understand about this degree of freedom in the next class. Do we understand this? Remember, if the atomicity of the gas or total kinetic energy of gas, for any gas, if I want to find the kinetic energy, remember the formula that we saw, 3/2 kT or 3/2 RT, that was transitional kinetic energy. If I want to find total kinetic energy, remember a gas molecules can move in transitional motion. It can also rotate. So some gas molecules also have rotational energy. Do we understand this? Some gas molecules also have rotational energy, whether it's transition energy or rotational energy. We will come to that. We will understand that. If I want to find the total kinetic energy, now remember this total kinetic energy consists of two types of kinetic energy. What are those two types of kinetic energy? One is known as transitional kinetic energy. Transitional kinetic energy के formula we have just seen. The other one is known as rotational kinetic energy. Do we understand this? The formula that we have seen up till now were only of transitional kinetic energy. If rotational component is also added, then the formula becomes like this. Instead of 3, I have F, the degrees of freedom. For 1 mole, it is 3. It is F by 2 RT. For 1 molecule, it is F by 2 KT. Remember, wherever there is molecule, you have key, you have K. Wherever there is mole, you have R. Do we understand this? Can I have some reason that we understand this? I'll give you a minute to win it. Please note it down before this minute goes away. Have you noted it down? Shall I move ahead? Time. You need time. Yes. Okay. I can understand sign language. I have done a PhD in sign language. I'll give you a minute. Note it down. This chapter is all about how many things you can remember in life. I'll give you a minute. Okay, I think we are done. So now it's my duty to move on to the next thing, and the most important thing. And the most important thing looks like this. The formula for the RMS velocity. The formula for RMS velocity. There are 3 different ways in this formula can be written. This is, oops, what I've done here. This is way number 1. This is way number 2. And this is way number 3. 3 different ways in which I can write this formula. 3 different ways in which I can write this formula. And how do we get to these ways? How do I get to these ways? I will leave it to you. How do I get to these ways? I will just give you a hint. The formula that we saw in the beginning was pressure was 1 by 3 rho into VRMS square. Do we understand this formula? Do we remember this formula? From here, I can find out the value of VRMS. From here, I can find the value of VRMS. VRMS, oops, I've written it wrongly. VRMS will be root over 3p by rho. Do we understand this? Then using ideal gas equation, we can write this formula 3p by rho, or p by rho can be written as RT by molecular mass, molecular weight. It can also be written as 3 times KT by mass of one molecule. What you got to remember is wherever you have R, you have mole or molecular mass. Wherever you have K, you have wherever you have R, you have molar mass. Wherever you have K, you have mass of one molecule. Do we understand this? And then we can see this simple formula. VRMS is directly proportional to root over T. Remember, this T is temperature in Kelvin. Please remember this. This T is temperature in Kelvin. This T is temperature in Kelvin. This molecular weight should be in kgs, SI units, not in grams. This Mass of one molecule should also be in kgs. Remember, temperature has to be in Kelvin. Do we understand this? Don't use ulta sida. Don't use ulta sida units, because if you use ulta sida units, you will get ulta sida answers. I'll give you a minute to note this down. What you have to understand here, bacha, is VRMS is directly proportional to root over absolute temperature, root over absolute temperature. Then you see two graphs. Do we see those two graphs? Have you written all this jiggy piggy that I told you? Have you written this jiggy piggy that I told you? Then, where is my thing? Where is my thing? Okay, it's here. Then you will have to see these two graphs and remember these two graphs, because a question will come straight away on these graph, and I hope you can see these two graphs. Yes or no? The one is between the first one is between VRMS and T. VRMS and T. We see VRMS is proportional to root over T, and therefore the graph looks like this. The second graph is between VRMS ka squared. I hope you see VRMS ka squared and T, and the graph is a straight line. Remember this graph. I'll give you a minute to win it. A minute to win it. A minute to win it. If you've written this down, please tell me so that I can move ahead in life. Life has to move ahead. Time has to move ahead. So let me move ahead in time and move ahead in life, and I write some important points about what? About VRMS. Point number one, important point number one. VRMS. The RMS velocity is directly VRMS is directly proportional to the root of absolute temperature, or VRMS ka square is directly proportional to absolute temperature. Remember, this temperature, this temperature, or this temperature, they have to be in Kelvins. Don't use degree Celsius or you will be doomed. You will be doomed. You will be doomed. Second formula, second thing that you must remember, VRMS is inversely proportional to 1 by molecular weight, or you can also write it root over 1 by mass of one molecule. It is inversely proportional. So if you have something, if you have some gas whose molecular weight is more, the RMS velocity is going to be less. Please remember this. Please remember this. Please remember this. Or you can write, if I talk in terms of VRMS ka square, you can write it as VRMS ka square is inversely proportional to 1 by the molecular mass, or 1 by the mass of one molecule of the gas. Remember the difference, see the difference, understand the difference. Here it is VRMS and here it is root. Here it is VRMS square, and therefore the root has disappeared. Please remember this. A minute to win it. Point number three and very important point. Point number three and very important point. Point number three and a very important point. Now look here. We have seen this formula of VRMS is equal to 3p by rho. 3p by rho. Now this formula is misleading because it lets it leads us to believe that, please listen to me very carefully, it leads us to believe that pressure and density also influence the RMS velocity. From this formula, you can see Vrms is directly proportional to root over pressure. Vrms is inversely proportional to root over density. Remember, that is not the case. That is not the case. In general, if I talk, Vrms only depends on the temperature of the gas. It does not depend on the pressure of the gas. It does not depend on the density of the gas. Now you will say, sir, the formula it is coming like this. But remember, beta, when I see this formula, I see the ratio of P by rho. So it does not depend on pressure alone and density alone. It depends on their ratio. If that ratio remains same, the RMS velocity remains same. And this ratio actually relates to the temperature, because from this ratio, I get the temperature. That means if I keep the temperature constant, pressure of the gas may increase, but similarly, the density of gas will also increase. So P by rho ka ratio will remain constant. So remember, the most important thing in life, Vrms does not depend on pressure and density of the gas. Pressure and density of the gas. It only depends on, and please remember this very clearly, it only depends on the temperature of the gas. If any book says that the RMS velocity depends on pressure, it is absolute nonsense. Do we understand this? Can I have some reason that we understand this? Because if I change the pressure, the density of the gas may also change. Okay. So if the density does not change, that means the temperature remains constant. So Vrms does not depend on pressure and density alone. It depends on the ratio of pressure and density, and the ratio of pressure and density can only change by changing the temperature. Please remember this. Please don't forget this. Please don't get confused. If you get confused, you are doomed to get -5. In this chapter, if you get -5, well, you have done absolute harakari of whatever we have done in the class. So please don't destroy everything that we have done in the class. Please take something out. I'll move ahead. I hope you have written this. Shall I move ahead in life? Yes, sir. No, sir. Then there are different types of speed. We have seen one speed, but there can be other speeds as well, and you can have a question based on that speed. The first type of speed is average velocity of all the molecules put together. And if I find the average of all the molecules, some molecules will be moving in this direction, but an equal amount of molecules will be moving in the opposite direction. And therefore, whenever I find the average of all the velocities, the average of all the velocities will always turn out to be zero. Will always turn out to be zero. Will always turn out to be zero. The average velocity is zero. The second type of velocity I have seen is RMS speed or RMS velocity. It is root over 3 P by rho. It is root over 3 RT by molecular mass. It is root over 3 KT by M ka root. Root over 3 is 1.732. So the RMS velocity other formula is, if you don't want to use root over 3, you can use root over K. You can use 1.732 in place of root over 3. Please note it down. Average velocity is 0. RMS velocity is this thing. Remember, RMS velocity is, first we take velocity, then we square it, then I take the average, and then I take the root. Do you remember this definition of Vrms? Yes or no? Please raise your hands and tell me that you remember this. Yes. I'll give you a minute to note this down. Please note it down. I guess you have noted it down. Shall I move forward? Then the next thing is mean speed or average speed. Remember, the first thing that we saw was average velocity. Velocity has direction. So this velocity and this velocity will get cancelled. But speed does not have direction. When we talk about speed, this speed and this speed will not get cancelled. There is no positive speed and negative speed. Speed does not get cancelled. So whenever I talk about average speed or mean speed, the mean speed is not zero. Average velocity is zero, but the average speed is not zero. And you don't have to understand how this formula comes. The formula is root over 8 by pi p by rho, or root over 8 by pi RT by molecular mass, or root over 8 by pi KT by M. So basically 3 in the previous formula has been replaced by 8 by pi, and when I put the values, the value of 8 by pi becomes 8 by pi ka root becomes 1.595. So you have to remember this 1.595. This is root over 8 by pi, and this is related to the mean or average speed. And this is how you have calculated the average speed. Remember, I have put the modular sign here so that this plus and minus gets negated and we have all positive values. Do we understand this? Please note it down so that I can move ahead. Have you noted it down? Okay. Then I have the third type of speed, which is known as most probable speed, VMP, most probable. Now, what do you mean by this most probable speed? Well, in a gas, molecules are moving with all possible speeds from 0 to infinity, not infinity, 0 to the speed of light. They can have all possible speeds. Now, this most probable speed is the speed with which the maximum number of molecules are moving. There is one particular speed with which maximum number of molecules are moving, and that speed is known as most probable speed. And in most probable speed, instead of 2, you have 3, as you can see. In place of 3, you have 2. 3 has been replaced by 2. Root over 2 is 1.414. So you have the formula as root over 2 RT by M, root over 2 KT by M, or root over 2 P by rho. Root over 2 is 1.4. So the formula becomes V most probable is 1.414 root over KT by M. Remember this most probable speed. Sometimes they also ask a question or give a question of speed of sound in a gas medium. Speed of sound in a gas medium is root over gamma P by rho, root over gamma RT by M, or root over gamma KT by M. This gamma is known as the ratio of specific heats. We will see what this gamma is, and the value of this gamma normally lies between 1 and 2 So remember these 5 speeds that we have seen. The first one was average velocity. Average velocity is 0. The second one was RMS velocity root over 3 p by rho. The third one was average velocity root over 8 by pi p by rho. The fourth one was most probable speed root over 2 p by rho. And the fifth one is speed of sound in a gas root over gamma p by rho. All the formulas are same. The numbers are different. In case of RMS, the number is 3. In case of average speed, sorry, the number is 8 by pi. In case of most probable speed, the number is 2. In case of velocity of sound, the number is gamma, and gamma lies between 1 and 2. Please note it down. I'll give you a minute to note it. Then what we can see is the relation between all these 4 speeds that we have seen. VRMS is the greatest. Then we have V mean, 8 by pi. Then we have most probable, 2. Then we have speed of sound. This is the order in which the speeds are. Point number 2 comes from point number 1, which we have already seen. Velocity VRMS divided by V sound. Velocity of sound is root over 3 by gamma. VRMS by V most probable is root over 3 by 2. A temperature is not possible at which the above order can be changed. All the speeds cannot be equal. The order will remain same at any given temperature. Any speed is proportional to root over absolute temperature. The graph is a parabola. We have already seen the graph. It is parabolic graph. Please note this down. I'll give you a minute to note it. Have you noted down these points? Yes or no? Okay. Since you have noted down these points, this is all theory that we had to do. And now we'll move on and see some questions that have come. And this is the first one in line. And I hope you can give me the answer for this. Question number 33, you can move your sheets and get to those questions. VRMS, V average, and VMP are the root mean square average and the most probable speed. Obeying Maxwellian velocity distribution, which of the following statement is correct? And the answer is 1, 2, 3, 4. What is the answer? The answer is 2. Yes or no? Yes or no? VRMS is the highest. Then we have V average. Then we have V most probable. Do we understand? Do we understand this? Yes or no? So the answer has to be B. See, if we understand questions clearly, the theory part clearly, we would be able to solve all the questions very easily. Shall I move on to the next one? This is the next one, and I'm hoping for an answer. According to kinetic theory of gases, The RMS velocity of the molecules of the gas is proportional to what? A, B, C, D, 1, 2, 3, 4. And the answer is T, T raised to the power half, T raised to the power square, T raised to the power 2, T raised to the power minus half. What is the answer? Plus 5, plus 4 or minus 5. What is the answer? No one knows the answer? Four. Very wrong. Arey gado. V is proportional to root over T. Do you don't know what is root over T? How can I write it? T raised to the power half. Don't you know this, bacha? Okay, if you don't know this, this is the answer. So the answer is B. Do we understand this? Minus half means it is going in the denominator. It does not go in the denominator, beta. It is directly proportional. Will you remember this now? Yes or no? Chalo, 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 chalo. We'll move ahead in life. We'll move ahead in life, and I'm waiting for this one. Again, you have your sheet. You can see it in your sheet. The average transitional kinetic energy of a molecule depends on what? Waiting for your answers, bacha. Question number 43 is what we're looking at. It depends on what? Pressure, temperature, volume, pressure and volume both. And the answer is 1, 2, 3, 4. And the answer is 2. It depends on the temperature. Yes or no? Yes, sir. No, sir. We will move ahead, sir. The more the number of questions you will do, the more you will understand the importance of theory that you have done. And we move on to the next question. Question number 49. Which of the following statement is not according to the postulates of the kinetic theory of gases, which is not a correct statement? Gas molecules are of small size. They're always in motion. There is no force between the molecules. None of the above. And the answer is, I don't see your hand because it is in the light. I can't see it. And the answer is 4. None of the above, because all of the statements are correct. So the answer is 4. You can only find out this answer. You can only find out this answer when you understand the postulates, and that is why we have done the postulates. As you can see, most of the questions that have come are already on the postulates. Again, one more question on the postulate. According to kinetic theory of gases at a given temperature, done, 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 done. A, B, C, D, 1, 2, 3, 4. According to kinetic theory of gases at a given temperature, at a given temperature, at a given temperature. Think, 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 think. At a given temperature, they are talking. And the answer is 3. All molecules have the same kinetic energy. Do we understand this? Yes, if you understand it, that means you have understood the entire concept of kinetic theory of gases. Well done, bacha. I was not expecting that you will give me this answer. Whether it was a fluke or a tukka, I am very happy. But I hope you have thought about it and not a fluke. You have thought about it now, or it was a fluke? Thought about it? That is very good. Then comes the next one, and let me see if you have the answer for this. If the RMS velocity of molecules of a gas in a container is doubled, what will happen to the pressure? Let us see. If the RMS velocity of the molecules in a container is doubled, what happens to the pressure? Now again, this question is a tricky one, and that is why I'm doing this. Now, remember, this question is also incomplete because it might not give you the complete information. Now, if I double the pressure, and if I look at the equation, and which is the equation that I am talking about, remember, I've told you that it does not depend on pressure. It does not depend on density. But look very closely, my bacha. PV is equal to nRT. Do we understand this? Yes or no? Now here, in a container, what we see is the volume will be same, yes or no? The number of moles is same, yes or no? The value of R is same, yes or no? R is universal gas constant. So, when I make the pressure twice, the temperature will also become 2 times, yes or no? If the temperature becomes 2 times, what happens to the RMS velocity? RMS velocity is proportional to root over temperature. If I make temperature twice, RMS velocity will become how many times? It will become 4 times. So the answer is A. Do we understand this? Yes or no? If the question was put like this, does RMS velocity depend on pressure? Then you will say no, it does not depend on pressure. It only depends on temperature, because I can increase the pressure in such a way that the temperature does not change. Do we understand this? Okay. And that is the reason I had given you this question, so that I can make a point very, very clear. And comes the next one. Question number 51. And here it's for you. Let's see. A box contains n molecules of a gas. If the number of molecules is doubled, what happens to the pressure? And the answer is A, B, C, D, 1, 2, 3, 4. What is the answer? Same. Decrease, double, triple. What is the answer, bacha? Answer is 3, which is it will be doubled. Yes, PV is equal to NKT. Make the number of moles on molecules twice. Pressure becomes twice. Do we understand this? Yes or no? Then I have this question again, a tricky one. Let's see if you can do this. In a container filled with a mixture of H2 and O2, hydrogen and oxygen. Question number 52. Let's see who gives me this one. Let's see. Confusing? +4 or -5 is the only number that you get. If you give it wrongly, it is straight away -5, not -1. But please remember this. A, B, C, D, 1, 2, 3, 4. I can't see your hand because your hand is in dark. Is in light. 1. RMS velocity of H2 molecules is mole. Yes, bacha, remember RMS velocity is inversely proportional to the molecular mass. Whosoever has less molecular mass will have more velocity. So this option is wrong. When I talk about energy, I talk about kinetic energy. It is 3 by 2 kT, 3 by 2 RT. So they are both same because temperature is same, because they are in a mixture. In a mixture, temperature has to be same. We have seen the formula for finding out the mixture temperature as well. So the option which is correct is option number 1. As you can see, most of the questions coming in this category are not numericals. They are based on your understanding of the topic and the postulates. And here comes the next one. You can see it in your sheet. Here it comes right in front. Question number 47. The RMS velocity of a gas molecule is C at temperature T. If the RMS velocity is increased to 4 times C, what will be the corresponding temperature? And I'm waiting for your answers. A, B, C, D, 1, 2, 3, 4. I can't see because it is in light. Get it in the dark. Yes, number 1, 16D. VRMS is inversely proportional to RMS proportional to root over T. You make temperature 16 times, then only the velocity will become 4 times. This is Van der Waals equation. Many a time it comes. That is why you must know it. Gases obey Van der Waals equation. Dung, 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 dung. More of chemistry rather than of physics. Normal temperature, normal pressure, high temperature, high pressure, high temperature, low pressure, all pressure and temperature. And the answer is, you might not know Van der Waals equation. It is valid at all temperature and pressure. Will you remember this, bacha? This is for you to remember. This is for you to remember. And now the actual equation, and the actual equation comes here. Please note this down. Please note this down, and the actual equation comes here in this question. The Van der Waals equation is which one? A, B, C, D. A, B, C, D. Van der Waals equation. Might not be knowing it, so I'll tell you it is the equation number 1 or A. P is replaced by P plus A by V square. V is replaced by V minus P. A and B are Van der Waals constant. That is equal to RG. That is how the equation is written. Please note it down. Physics and chemistry both common. Physics and chemistry both common. Physics and chemistry both common. So remember it. It is valid at all temperatures and all pressures. If you have done this, I'll move on to the next one, which is the next problem, which is problem number 56. If T is the temperature at which the RMS velocity becomes double of its value at 100 degrees Celsius, then how much is the temperature? Waiting for your answers. A, B, C, D, 1, 2, 3, 4. And the answer is, velocity has to become 2 times. So temperature has to become 4 times. Yes or no? So if the initial temperature is 100, the final temperature has to be 400. Yes or no? Yes, sir. So the answer is 400 degrees Celsius, sir. But that is wrong, sir. Because it is degrees Celsius, sir. And the temperature is not in degrees Celsius, sir. And that is why it is wrong, sir. So do we understand it, sir? Temperature has to be in Kelvin. Do we understand this? So the initial temperature is not 100 degrees Celsius. It is 100 plus 273. It is 373 Kelvin. Do we understand this? That was the reason this question was given. 373 Kelvin was the original temperature. 373 was the 373 Kelvin was the original temperature. This temperature has to become 4 times. So I multiplied by 4. That will be the answer in Kelvin. but the answers are given in terms of degree Celsius. Only one answer is coming anywhere close to that, and that one answer which is coming close to that, which is the correct answer, is which one? It is option number 4, and the answer is 1219 degrees Celsius. Do we understand this? Yo, we understand this? The problem here, not a problem here. The question was given in degrees Celsius. We had to convert it into Kelvin. That was the only thing that we had to do here. I'll give you one more. Remember, there are a lot of questions in this exercise. I can't do all. I can only do a very select few. The rest of them is on you. And I hope you can do it today and tomorrow. Because from tomorrow we will move on to the next topic, which is the degrees of freedom, F. This is the next one which is coming in line. N2 molecule is 14 times heavier than H2. At what temperature will the RMS speed of H2 be equal to the speed of N2 at 27 degrees Celsius? Let's see who gives me this. A minute, 2 minutes. Well, the answer is 421.4 Kelvin or degrees Celsius. I think there might be something wrong with the thing. Let me check it out. How you have to do this? So velocity of N2, I can write it as root over 3 times T divided by molecular mass of N2. Velocity of H2, I can write it as 3 times. Okay, I know the value of this T. This is given as 27 degrees Celsius. So 27 plus 273 becomes 300. So I'll just write here 300. Do we understand this? 3 into 300. Here it will be 3 times T divided by molecular mass of H2. Now molecular mass of H2, nitrogen is 14 times. So I can write here at 14 times molecular mass of H2. I will just divide these two equations and I will get the answer. Can you do that for me? So what will I get? I don't have space over here. Just divide it and you will get the answer. It is as simple as that. I will not move any further into this because this will just be a waste of time. I should not waste any time and I should move on to the next question so that you can have an idea of how it is done. Question number 65. If the total number of H2 molecules is double that of O2 molecules, then the ratio of total kinetic energies of H2 to O2 at 300 Kelvin is how much? Remember, RMS speed, kinetic energy, all these things. 4, 1 to 16. Gone mad or what? Temperature is same, bacha. Only the number of molecules have changed. Temperature is same. So because of same temperature, they will have same kinetic energy, but there are number of molecules are not same. Number of molecules of H2 is 2 times. Therefore, the ratio will be 2:1. Do we understand this? Okay, what I'll do is, I think you might be getting a bit confused. So I'll just give you a small dose. I call it a small dose. This is nothing new. We have already done it, bacha. I'll just try to make more sense out of it. And please, I hope you can see this. I hope you can see my screen. Yes or no? Okay. Just remember this. Just remember this. Don't get confused. Just remember this. Number 1. Transitional. I am talking about transitional. Transitional kinetic energy per mole of any gas at any temperature. Transitional kinetic energy per mole is 3/2 RT. Do we understand this? Okay. Number 2, I can write this equation in a different way. Total transitional kinetic energy. So total transitional kinetic energy will be 3/2 multiplied by N, where N stands for the number of moles. Do we understand this? Transitional kinetic energy per molecule. Transitional kinetic energy per molecule is 3/2 kT. Do we understand this? Then from here I can write total transitional kinetic energy as 3/2 NKT. Now what you got to remember, for any two gases, if the temperature is same, for any two gases, if the temperature is same, then quantity number 1, and I have written the quantity wrongly here, so I will just correct it. For any gas, any two gases at the same temperature, quantity number 1 and quantity number 2 will be same. Do we understand this? These two quantities will be same for all gases at same temperature. Do we understand this? But when you talk about quantity number 1 and quantity number 2, in quantity number 1 and quantity number 2, you have number of moles coming here, and therefore the total kinetic energy will be different. Do we understand this? And that was specifically, that was the question that was asked in this question, and that is why the answer is 2:1. Can I have some reason that we have understood this? On that note, I will wind off this class. I will leave the rest of the questions for you to decide. In the next class, we will be going ahead with degrees of freedom, and you will enjoy that part because it is very simple. So be attentive, be present in the class, and I'll see you in the next class. Till then, have a nice day. Enjoy your day. Best of luck for your exams. Take care. Bye bye, bacha.